First I should say this isn't a report on my project progress. Afraid I've been a bit busy with other projects and work on the house and so on, and haven't done a lot of work on that recently, but I am still very enthusiastic about it, and it's still an important priority. This is just a remake of a video I got up explaining how double focusing works, because I saw some people were looking at it and the video wasn't terribly good, so I thought I'd make a better one, or at least the first one was worse than this one. Okay, so this is without double focusing, just a simple mass spectrometer. We have an arrangement where the ion comes from the source, and it's in a beam. It's bent by a magnet, and then it goes through a slot onto a detector, and only ions of the required mass will be able to pass through this route and hit the detector. So just to look at how that works, the ion velocity is given by this relationship. This is the charge of an electron, that's the charge on the ion. VA is the accelerating voltage, and this is the mass. This comes from Newton's equation, v squared equals u squared plus 2as, with u set to 0. So if we look how the path works when it's deflected by the magnet, we have two equations. This is the force on the ion from the magnet, charge of an electron, the velocity and the flux density, and this is the force on the ion due to centrifugal force, mass times velocity squared divided by the bend radius. So these two must be equal for it to bend round the radius, and so if we combine those two equations we get this, and so we see B is proportional to the mass if V is constant. But we do know from this here that the V isn't constant. The V depends on the value of the mass. So when we take that into consideration, we get B is proportional to the square root of m, in fact m over q. So this doesn't really matter, it just means the number crunching in the mass spectrometer has got to take this square root relationship into account. Okay, so another thing we need to have is a simple focus. The ions will diverge when they come from the ion source, and really we want to make all the ions that come from it useful. So really you don't just want to skim them off into a narrow beam, you want to try and focus all of them onto the detector. So where the ions approach the detector, we want a narrow focus like this at the slot, which is used for discrimination, and we don't want a wide beam like this, because as the beam is bent by the magnet, and as you scan, this beam moves about, and so you won't get a narrow spectrum unless you have a good focus. So if this is the actual mass of the ion in the centre, with a poor focus you get this sort of thing, and with a good focus you get this sort of thing. So we can see that this simple focus we spoke about is necessary in order to get a narrow spectrum like this. Well, there's another thing that affects the spectrum width. As we were saying, we have the velocity from the ion source is proportional to 1 over the square root of m. Well, this is really saying that it's the energy of the ion that's constant when we come out of the ion source. The kinetic energy is equal to half mv squared, so you can see this relationship here implies a constant energy. So okay, that means velocity changes with the mass and the kinetic energy is nominally constant. But the problem is that although the kinetic energy is nominally constant, it's not exactly constant. There is a noise spread around the centre value. This is due to various things, due to the fact that the molecule or ion will have random motions before it's ionised, and also if we're using an electron beam to ionise it, the electrons have got energy, and so there are all sorts of random things going on when the electrons hit the molecule to ionise it. So we need to make the the mass selector independent of energy. Well, if we look at this equation here, the relationship between the magnet flux and the mass, you can see V's in there, so you see if there's a random movement of V, it will affect this relationship. But also we can see from this relationship here that for a fixed mass and a fixed flux density, that there is a direct relationship between R and V. So as V varies, R must also vary. The bend radius is proportional to the velocity. Notice how the entry and exit paths of the ion are tangential to the circumference of this arc, the bend. So if we want to make the mass filter independent of the velocity for a given mass, what we need is a magnet pole that can support different bend radiuses, where the bend radius is proportional to the velocity, and for each path, each curve, the tangential entry and exits of the ion must point towards the centre of the ion source and the point of discrimination on the ion detector. Well, in order to make this focusing that's independent of energy work, another thing we need to do is we need to be able to get a measurement of what this energy is. We know that the ion path through the magnet is going to be different. We can't make that independent of the energy or the velocity, so we're going to have to measure what it is. Well, the way we can do that is with an electric field. So here we have curved metal plates with a voltage between them causing an electric field, and the ion comes in and it is bent through an angle. We see 90 degrees here due to the electric field. So the electric field is causing a force, causing the ion to accelerate along this radial axis towards the centre of turn, so that causes it to bend through 90 degrees. So let's see what are the things that will determine what path this ion takes as it goes round this bend. We know that the velocity coming in, V in, is proportional to 1 over the square root of m. We get this from the ion detector, and we also have the equation of motion around the bend, very similar to what we had with the magnet. Here we have mv squared over r. This is the centrifugal force term, and that must be equal to QE. This is the force on the ion due to the electric field. Q is the charge of an electron, the charge we have on the ion, and E is the electric field. That's this voltage divided by the distance here. So a thing we can see straight away is that this mv squared here is a constant, providing this is valid. It's fairly clear that if V is proportional to 1 over the square root of m, then this is going to be a constant. So this here is all a constant, and this is a constant, so that means that R must be constant. So what we're saying is, providing this relationship is valid, then the ion will come in and it will always be bent through the same angle. So we can just adjust this voltage so it's bent through exactly 90 degrees. And whatever mass comes out of the ion detector, it will always be bent through 90 degrees. But if this relationship is not valid, that will cause this to be bent through a different angle. So if the velocity is slightly higher, it will be bent a little bit less. So this dispersion we get here, this difference in the bend angle, is a measure of the energy of the ion, or for a particular mass it's a measure of its velocity. And so this is what we need in order to arrange for a different path through the magnet depending on the energy. Right, so if we have an arrangement like this, this is our double focusing arrangement. We have this electric sector, the ion comes in, it's bent through 90 degrees, and depending on the energy it comes out at a different angle. And so really you can see what we need to do is we need to align all these geometries together. This is the magnet, and the magnet pole shape has been arranged so that the ions of a lower energy bend round this radius, the ions of a higher energy bend round this radius, and the magnet pole pieces have been so arranged that the sector through which the higher energy ones are bent through is a slightly larger angle, and so we can arrange that these two paths converge to the same point on both sides of the magnet. So providing all these things are aligned correctly, then this will give you a path which ends up at the same point here on the ion detector, regardless of what the energy is. A thing we haven't considered here is that the simple focus, like an optical focus we spoke about, which of course you need in order for the diverging paths of the ion from the ion source to arrive at the same point here, that focus must not be upset by this arrangement, and so that is a complication as well. We won't go into that, but of course that does need to be done. And there are standard alignments of this that are used commercially to make this work. We can have a slit here which will only allow ions through that are within a certain energy band, so if the energy is outside the range that we can compensate for, then they will be skimmed off. So that is about it, how double focusing is done on commercial mass spectrometers, or one of the ways. It's done in other ways. But for me, the problem with this is a very difficult thing to make. It's got all sorts of difficult mechanical geometries that have got to be correctly aligned, and it will only work if this thing's precisely made and precisely aligned. And so this mechanics has got to be exactly right. And this is a thing it's a bit difficult for me to do in my garage. So I'm looking for a way that I can make a sort of poor man's double focusing mass filter. And so a thing I've been looking at is an arrangement like this. So the ion path comes along and it's bent through a 90-degree path here with the between the poles of the magnet, just as we saw in a simple mass spectrometer, a mass filter without double focusing. But an additional thing we've got here are there are some electric field plates which are present all the way around the path that the ions bent due to the magnetic field. So what we're trying to do is to have an electric field wherever there's a magnetic field, and we adjust the electric field so the force due to it is opposing the force from the magnetic field. So this means the magnetic field has got to be twice as strong as it would otherwise have to be for a given accelerating voltage. Now if we look how this works, these are the equations. So here we have the force due to the magnetic field, and here we have the force due to centrifugal force, and here we have the force due to the electric field. So you can see if the electric field isn't put in, then we have the problem here that we had before. If we have a 1% change in velocity, this term changes by 2% and this term changes by 1%, so we can see it's dependent on velocity for a fixed mass. If we put this term in due to the electric field and we make these two terms equal, you can then see that for a 1% change in velocity, although this term changes by 2%, it's only half of the right hand side of the equation. So the whole right hand side of the equation only changes by 1%, as does the left hand side. So providing mv squared upon r is nominally equal to QE, then we balance out the effects of small changes in the ion energy. The problem with this is that B must be doubled. Of course, you may want to keep flux density constant and reduce the velocity in the ion accelerator. Normally, the maximum flux density is limited by the power of the electromagnet, so you may want to reduce the velocity. Of course, if you do that, then that causes noise to increase, because there are the various noise sources in all sorts of ways, and really the smaller the velocity, the bigger the noise in comparison to the velocity. Well, be interested to hear what anyone thinks about this. I initially hadn't seen this technique used anywhere, but I did actually find a paper that described this, so possibly this technique has been commercially used. I'm not sure. Anyway, thank you for watching.